Imagine a world where the very idea of calculation was,
Hmm.
well, it was fuzzy, right? Vaguely understood as just, something a human could maybe do with a pencil and paper.
No real precision to it.
Exactly. What if nobody had ever truly pinned down what a mechanical step actually was?
Yeah.
And then, boom, 1936. A young mathematician publishes this paper.
Alan Turing.
Yes. And it doesn't just define computation. It lays the conceptual groundwork for every computer, every single algorithm, all the software that exists today. It's basically the origin story of our entire digital universe.
It really is foundational.
Hey everyone, and welcome to The Deep Dive. This is the show where we take these monumental ideas, often from really key papers, and we sort of unspool them into what we hope are fascinating, accessible conversations. I'm Alex.
And I'm Jordan.
And I am genuinely eager, maybe even a bit buzzed, to explore the absolute blueprint of computation today.
And I'm ready to unpack the logic, the foundational thinking behind modern computing. Because today, we're not just looking at some historical document filed away somewhere. We're stepping back in time, really, to analyze the theoretical engine, the core idea that drives our digital world.
We are diving into a truly monumental piece of work. It often goes unrecognized outside, deep academic circles. But it's A.M. Turing's 1936 paper. The title is On Computable Numbers, with an application to the Entscheidungsproblem.
Quite a title.
It is. And look, this isn't just some dusty old tech paper from, almost 90 years ago now. It is, and I don't think this is hyperbole, the conceptual genesis of the computer as we know it.
Absolutely. The blueprint.
And what's just so profound, I think, is that Turing wrote this groundbreaking framework nearly a decade before the first proper electronic digital computers even flickered to life.
Mm-hmm. Predating ENIAC and the others.
Yeah. It just speaks volumes, doesn't it? About the sheer power of abstract thought. To define something so fundamental to our modern lives with just, logic and pen on paper.
It's incredible. And to really appreciate the brilliance, the lasting impact of Turing's paper, we first need to understand the intellectual landscape, the context. What were the huge problems he was actually grappling with?
Right. What was the big question?
Well, at its very core, Turing set out to rigorously define what it actually means for something to be computable.
Computable. Okay.
Before his work, this idea, computation, it was often understood pretty vaguely. People saw it as something humans did, maybe with pencil and paper following some kind of instructions.
Like long division, maybe?
Kind of, yeah. But there was no formal, universal, clearly defined boundary for it. And without that clear boundary, mathematicians couldn't even really begin to discuss the limits. What couldn't be calculated.
Okay. You need the definition before you can find the edge cases.
Exactly. The paper itself states it pretty clearly. It says, the computable numbers may be described briefly as the real numbers whose expressions as a decimal are calculable by finite means.
Calculable by finite means. Okay, that sounds important.
It's the key phrase. But it was also the crux of the vagueness. What exactly constitutes finite means? What does calculable truly imply in a purely mechanical sense?
Right. Is it just what a human can do? Is there a limit?
Precisely. So Turing's goal, his really audacious goal, was to take this implicit sort of intuitive human understanding and make it explicit, formal, and totally unambiguous.
Make it concrete.
Make it concrete. And he recognized that while his paper focused on computable numbers, the underlying challenges were the same for computable functions or even logical predicates. Are they decidable?
So numbers were just the starting point.
He chose numbers for explicit treatment, as he put it, because it involved the least cumbrous technique. Basically, it was the most elegant and straightforward path to demonstrate his radical ideas.
Gotcha. The cleanest example.
Exactly.
And then there's that other massive problem right there in the title.
Yeah.
The Entscheidungsproblem. Did I say that right?
Close enough. Entscheidungsproblem, yeah. German for decision problem.
Decision problem.
Okay.
And this wasn't just some little mathematical puzzle, was it?
Oh, no, not at all. This was a foundational grand challenge. It was posed by the legendary mathematician David Hilbert way back in 1900, actually, at the International Congress of Mathematicians.
Hilbert. Okay. Big name. What was the challenge?
Hilbert asked, could there possibly be a general mechanical process, an algorithm, basically, though they didn't quite use that word in the same way, then
Right.
determine for any given mathematical statement or logical formula whether it's true or false, or even just provable within a formal logical system.
Wow. Okay, hold on. A general process. For any statement.
Any statement, true or false, provable or not.
That's huge. Think about the sheer ambition of that question. It's like asking for a universal algorithm for truth.
Pretty much, yeah.
If something like that existed, it would essentially give you a definitive answer to all mathematical questions. Like a kind of, I don't know, omniscient truth machine.
That was the dream.
So why was this such a monumental deal? What was going on?
Well, in the early 20th century, mathematics was kind of grappling with a profound foundational crisis. Logicians, mathematicians, they were building these vast, intricate, logical systems.
Like Russell and Whitehead's Principia Mathematica.
Exactly like that. But they lacked absolute certainty about their consistency, their completeness. Could these systems prove everything true? Could they accidentally prove something false? Hilbert's program aimed to put all of mathematics on this unshakable, purely mechanical foundation, resolve all disputes.
The ultimate logical certainty.
That was the goal. But, and here's the catch, without a concrete, universally accepted definition of what a machine was or what a mechanical process really meant.
This Brit's dream was stuck.
It remained elusive, yeah. An abstract hope. It was this huge philosophical and mathematical void that just urgently needed filling.
And Turing stepped in.
That's precisely it. What was truly broken, what was missing before Turing, was that precise formal definition for calculable by finite means, or as logicians at the time called it, effective calculability.
Effective calculability. Okay.
Without a concrete definition everyone agreed on, how could you even start to prove fundamental limits? Limits on what could be computed or decided.
Right. It's like trying to measure the speed of light without defining speed or light.
Exactly that. You need a clear benchmark, a boundary. Turing cleverly saw that the underlying problems for numbers, functions, predicates, they were all linked. This lack of a rigorous definition left this gaping hole in mathematical logic.
Making it impossible to talk about limits.
Right. And the intellectual climate, the early 20th century, was absolutely ripe for this kind of breakthrough. We can't really talk about Turing without mentioning Kurt Gödel again.
Gödel's incompleteness theorems. Yeah.
Right, which Turing himself explicitly references in the paper. Gödel's work had already sent these huge shockwaves through the mathematical world just a few years earlier in 1931.
What did Gödel show? In simple terms.
Gödel proved that within any sufficiently strong axiomatic system, think of the rules underpinning arithmetic, there are statements that are true, but that cannot be proven within that system.
Yeah. True, but unprovable.
And he also showed that such systems can't prove their own consistency. They can't guarantee they're free from contradiction using only their own rules.
Okay, so that already showed limits to formal systems.
Huge limits. It suggested that Hilbert's dream of a fully self-contained, provable mathematical universe might just be fundamentally unattainable.
And then Turing comes along.
Yeah.
But wasn't someone else working on this too?
Yes. And this makes the historical tapestry even more fascinating. While Turing was working on his ideas in Cambridge, over in the U.S., the American logician Alonzo Church was independently developing his own formal definition of effective calculability.
Independently? Wow.
Completely independently, using something very different called lambda calculus. It's a system based on function definitions and applications.
Lambda calculus.
So?
Still fundamental in computer science today.
Absolutely. And what's remarkable is that Church reached similar conclusions about the Entscheidungsproblem, Hilbert's decision problem. He also concluded it was unsolvable.
Same conclusion, different method.
Very different method. Turing's was based on this idealized machine, Church's on this abstract calculus, but they arrived at the same answer. This parallel development isn't just a cool historical footnote.
No, it shows something bigger.
It powerfully highlights how pressing, how universal the need was within the mathematical community to formalize computation and provability. Two brilliant minds, different continents, different approaches, same fundamental problem, same answer. It was clearly a question whose time had come.
So it was against this backdrop, this sort of intellectual crucible, as you called it, that Turing really made his mark. Hilbert's program, dreaming of this perfect mechanical foundation for math.
The universal truth machine.
Yeah. Imagine resolving every dispute, proving every conjecture, the ultimate logical certainty. But like we said, without defining machine or mechanical process, it was just a dream.
An aspiration.
And Turing's 1936 paper was the direct, brilliant, and frankly deeply satisfying response to that void. It literally gave the machine a face, a precise formal identity.
It defined the terms of the game.
It really did. It was like going from just vaguely dreaming about flying to suddenly having these detailed blueprints for an airplane.
Mm-hmm.
It made the abstract concrete. And here's where Turing introduces his absolute stroke of genius, the very core of his solution. The computing machine, what we now all call a Turing machine.
The Turing machine, yeah.
He starts with this incredibly relatable, almost disarmingly simple analogy. He says, we may compare a man in the process of computing a real number to a machine.
Human as machine.
Yeah. So picture this. Imagine a really meticulous accountant working diligently, maybe in a quiet room. They've got this infinitely long scroll of paper stretched out in front of them.
That's the tape.
That's the tape. And they can only focus on one tiny section, one number or symbol at a time.
The scanned square.
The scanned square, exactly. Now, this accountant, they're not just scribbling randomly. They follow a very strict, finite set of rules. And crucially, they only have a finite number of distinct states of mind.
M configurations, he called them.
M configurations.
Yeah.
Right. And their every action, writing a new number, erasing an old one, maybe shifting their focus left to right along the scroll.
All determined.
It's entirely and deterministically governed by their current state of mind, their M configuration, and the symbol they're currently looking at on the scanned square.
It's elegant. It strips computation down to its bare essentials.
It really does. It captures the absolute essence of what human computation, when you break it down, fundamentally looks like. Methodical, finite steps, step by step.
Okay, so let's get a bit more specific about the anatomy of this abstract machine, pulling directly from Turing's paper, because the rigor here is key.
Lay it on us. What are the parts?
All right, so first, you have finite states, or M configurations. Think of these as the machine's internal modes or conditions. It can only be in one of a limited number of states at any time.
Finite states. Crucial for it being mechanical, right? Not magic.
Exactly. It makes it predictable and fully describable. Second, the infinite tape. This is the machine's memory or workspace.
The accountant's...
Precisely. Divided into squares, each holding one symbol. Now, the infinite part is a theoretical abstraction, obviously.
Real computers don't have infinite memory.
Right. But it's essential for proving the ultimate computational power. It means the machine isn't limited by storage capacity in theory.
Okay. Infinite tape. What else?
Third, the scanned square and symbol. At any moment, the machine is focused on just one square on the tape and the symbol written there. That's the only thing it's directly aware of.
One symbol at a time.
One symbol. Fourth, implicit memory through state change. Even though it only sees one symbol, it can effectively remember past symbols by changing its internal state, its M configuration.
Okay. The state holds the memory of what it's seen.
In a way, yes. It allows sequential processing. Fifth, configuration and behavior. The machine's current state plus the symbol it's scanning that pair completely determines what it does next. No ambiguity, no randomness.
Determined.
Totally. And finally, sixth, the elementary operations. The machine can only do a few simple things. Write a new symbol, erase a symbol, shift the scanned square left or right one step, and change its internal state.
Right. Erase, move, change state. That's it.
That's the core set, and the sequence of figures it prints during this process that forms the decimal of the real number which is being computed.
Simple actions, complex results.
That's the idea. Now, Turing also carefully defined different types of these machines. This is important for understanding their capabilities and, crucially, their limitations.
Okay, what types are there?
First, there are automatic machines, or A machines. These are fundamental. Their motion is completely determined by the configuration. No human steps in, no external choices. Once started, it just runs based on its rules.
Purely mechanical.
Purely mechanical. Then, a specific subtype, computing machines. These are A machines designed specifically to print figures, which Turing defined as zeros and ones, maybe along with some symbols of the second kind, like scratch notes for its own process.
So outputting binary numbers.
Essentially, yeah. If you give a computing machine a blank tape and the right starting state, it computes a sequence, effectively a binary decimal.
Okay.
And this leads to a really critical distinction. Circular versus circle-free machines.
Circular and circle-free. What's the difference?
A computing machine is called circular if it only ever prints a finite number of those zeros and ones. It either just stops, halts, or it gets stuck in a loop, moving around but never printing any more useful output.
Okay, so it finishes or gets stuck doing nothing useful.
Right. In contrast, a machine is circle-free if it keeps printing new figures indefinitely. It generates an unending sequence.
It just keeps computing forever.
And Turing defined the computable sequences, the infinite decimals he was really interested in, as precisely those sequences that can be computed by these circle-free machines.
So computable means it can be generated forever by one of these non-stop non-stopping, non-looping machines.
Exactly. And this distinction between circular and circle-free, it becomes absolutely central when we get to the halting problem.
Got it. Holding on to that. So he defined the machines, their types. Did he explain how to, like, build one? Theoretically.
He did. He didn't just stop at defining them, he meticulously laid out how to describe them. He used tables. Think of them like instruction sets.
Like a program.
Exactly like a program. A table defines the machine's behavior for every possible combination of its current state and the symbol it's reading. He even gives detailed examples how to build a machine to compute 0101010, or a more complex one like 0101010101.
Showing his work.
Absolutely. Step-by-step definitions based on state and symbol.
Okay, but describing complex machines with these tables must get huge, right?
He could, yeah. So to make things more manageable, Turing introduced abbreviated tables or skeleton tables. These are like predefined chunks for common processes.
Like functions or subroutines in coding today.
Precisely. Things like copy this sequence, compare these two sequences, erase everything here. You can see the direct line to modern programming abstraction right there.
Wow. Okay, so reusable blocks.
Reusable blocks. But here's the really revolutionary leap, the mind-bending part. These tables, which define a whole machine's behavior, can be written down in a totally standardized way, a standard form.
A consistent format for any machine description.
Exactly. And this standard form, which is basically just a long string of letters and symbols, he called a standard description, or SD.
SSD, like the source code.
Kind of, but then he takes it even further. This SD, this textual representation of an entire computing machine, can then be converted incredibly into a single unique number, a description number, or DN, just by systematically replacing the letters and symbols with digits according to a scheme.
Wait. You can turn the entire description of a machine, its whole program, into one number.
One unique integer. Think about what that implies. Every possible computation, every algorithm, every Turing machine, even the ones that run forever, can be given a unique numerical identifier, a serial number for computation itself.
Let that sink in.
Wow.
That's not just a coding trick. That feels deeper.
It's profoundly deep. This is the insight that computation itself can be represented as data. A program is just a number.
Program as data.
That's the bedrock concept. It's why software exists. It's why a computer can load and run any program you give it, because the program is just data represented by a number or a sequence of numbers. This is what makes the universal computing machine possible.
Universal machine. Okay, you mentioned that. That sounds like the main event.
It really is.
So speaking of profound insights, this is arguably the most, breathtaking idea to come out of the whole paper. The universal computing machine.
The UTM.
Turing proved mathematically that it's possible to invent a single machine which can be used to compute any computable sequence. What does that actually mean for us, sitting here with our laptops and phones?
Okay, picture this. It's not a machine designed for just one job, like only adding numbers or only printing 0101.
Not a specialized tool.
No. This is a master machine, a meta machine. Its job isn't to compute a specific thing, but to compute whatever any other Turing machine could compute. You feed it the description, that standard description, or even better, that description number, the DN we just talked about, of any other possible Turing machine.
You give it the number representing another machine.
Exactly. And this universal machine reads that number, understands the rules of the machine it describes, and then perfectly simulates that machine's behavior on some input. It literally becomes whatever computational process you describe to it via its number.
Whoa. Okay, so it's like a chameleon computer.
That's a good analogy. Or think about it like this. Before this idea, maybe you needed a different special projector for every single movie you wanted to watch.
Right, a projector hardwired for Star Wars, another for Casablanca.
Kind of. But Turing essentially invented the concept of a single universal projector that can show any movie you give it, as long as the movie comes on a standardized film reel. That's the description number.
Ah, okay, the format.
Right. This single universal machine is the direct conceptual ancestor of every general-purpose computer we use today. Your laptop, your phone, the servers in the cloud.
They're all universal machines.
They are practical implementations of Turing's universal machine concept. They take program code, which is basically a description number in a complex format, and they execute it, simulating the specific computation the code describes. It's the essence of programmability, software changing hardware function.
Mind blown. Okay, so The universal machine is incredibly powerful, but didn't the paper also talk about limits, things that can't be done?
It absolutely did, and this is just as important. While the universal machine shows incredible possibility, Turing's paper also revealed these profound, unshakable limits to computation. This brings us to what's now famously called the halting problem.
The halting problem, I've heard of this. This is big.
It's fundamental. Turing proved there is no general process for determining whether a given number is satisfactory or not.
Mhm.
Now remember what satisfactory number meant.
The description number for a machine that doesn't get stuck, the circle-free ones.
Exactly. A DN for a circle-free machine, one that keeps printing figures indefinitely, never halts or gets stuck in a non-productive loop. So, the halting problem is precisely this. You cannot create a general algorithm, a universal decider that works for all possible programs to tell you whether an arbitrary program will eventually stop or if it will just run forever.
You can't write a program that can reliably predict if any other program will crash or finish.
In essence, yes, not a general one that works for every single case.
But why not? That seems like something a computer should be able to figure out.
It seems intuitive, right? But he proved its impossibility using this brilliant technique called a diagonal process argument. It's similar to how Georg Cantor proved that real numbers are uncountable.
Diagonalization. Okay, how does that work here, roughly?
Okay, simplify it way down. Imagine, just for argument's sake, that such a general halting detector program did exist. Let's call it halts P, where P is the description of another program. Halts outputs true if P halts and false if P runs forever.
Okay, hypothetical halts program exists.
Now, using this halts program, you could construct a very specific kind of devious new program. Let's call it perverse.
Perverse, I like it.
Perverse takes the description of any program, let's call it X, as its input. Inside perverse, it first runs halts X.
Okay, it checks if X halts using our magic detector.
Right. Now here's the twist. If halts X returns true, meaning X halts, then perverse is designed to immediately enter an infinite loop and run forever.
Oh, sneaky.
But if halts X returns false, meaning X runs forever, then perverse is designed to immediately halt and finish.
It does the opposite of whatever the input program does.
Exactly. Now for the killer question. What happens if we feed the description of perverse itself into perverse? So we run perverse.
Perverse. Okay, let's trace it. Perverse first calls halts perverse.
Right. Now there are two possibilities for what halts perverse could return. Possibility 1. Halts perverse returns true.
Meaning perverse is predicted to halt.
But if halts perverse is true, then according to the definition of perverse, it's supposed to enter an infinite loop and not halt.
Contradiction. It halts if it doesn't halt.
Exactly. Okay, possibility 2. Halts perverse returns false.
Meaning perverse is predicted to run forever.
But if halts perverse is false, then the definition of perverse says it should immediately halt.
Another contradiction. It doesn't halt if it does halt.
Precisely. In either case, we get a logical impossibility. A paradox. What does that mean?
It means our initial assumption must be wrong.
Exactly. The initial assumption was that a general halts P program could exist in the first place. Since assuming it exists leads directly to a contradiction, such a program cannot exist.
Wow, okay. That's clever. So no general algorithm can solve the halting problem for all programs.
Correct. And this fundamental impossibility also extends to related problems, like figuring out if a machine will ever print a specific symbol, say 0, infinitely often. It sets this clear, unyielding boundary on what any computational process, any algorithm, can possibly achieve.
Okay, so the halting problem is unsolvable. How does that connect back to Hilbert's big question, the Entscheidungsproblem?
Ah, this is where the two colossal threads of the paper just weave together beautifully, or maybe tragically for Hilbert's dream.
How so?
Because there's no general mechanical process to determine if a Turing machine will halt, that's the halting problem we just discussed, Turing could then conclusively show that the Entscheidungsproblem, Hilbert's decision problem, also has no solution.
So the unsolvability of the halting problem implies the unsolvability of the decision problem.
Precisely. Think about the chain of logic. Suppose, hypothetically, you could solve the Entscheidungsproblem. Suppose you had Hilbert's magic truth machine that could tell you if any mathematical statement was provable or not.
Okay, imagine we had that magic box.
Well, you could then frame the question, does this specific Turing machine M halt when given input I as a formal mathematical statement within a suitable logical system?
You could express the halting question mathematically.
Right. Then you could feed that statement into your hypothetical Entscheidungsproblem solver, your magic truth box. It would have to give you a definitive yes, it's provable that it halts, or no, It's provable that it doesn't halt, or maybe it's unprovable.
And that would tell you if the machine halts or not.
Exactly. If you could solve the Entscheidungsproblem, you could use it to build a procedure that solves the halting problem.
But we just proved that the halting problem is unsolvable.
Bingo. Since we know the halting problem is impossible to solve generally, the premise that allowed us to solve it, the premise that a general solution to the Entscheidungsproblem exists, must also be false.
So Hilbert's dream of a universal truth machine, impossible.
Fundamentally impossible by any mechanical, algorithmic means that Turing defined. It was a profound, definitive no to that grand challenge. A true mic drop moment in the history of logic and mathematics. It reshaped the landscape, showing inherent, inescapable limits to what can be mechanically decided.
Wow, okay. So universal machine, yes. Universal truth machine, no. Limits are real. But despite these limits, the paper also said that lots of things are computable, right?
Oh, absolutely. Despite these profound limits, Turing was careful to demonstrate that the class of computable numbers is, in his words, so great. It covers a vast and powerful range of numbers crucial to math and science.
Like what, for example?
Well, he showed that the real parts of all algebraic numbers are computable.
Algebraic numbers, remind me.
Those are numbers that can be a solution to a polynomial equation with integer coefficients. Simple examples are like the square root of 2 or the golden ratio. More complex ones too, all computable.
Okay, what else?
Also, the real parts of the zeros of Bessel functions. These are important, complex functions used all the time in physics and engineering, describing things like waves or heat conduction. Their key values, computable.
Useful stuff for scientists and engineers.
Definitely. And perhaps most famously, those constants we all encounter in math class, pi and Euler's number E.
Pi and E are computable, but they go on forever.
They do. But computable here means there's a definite algorithm, a Turing machine, that can, in principle, calculate their digits one by one to any desired precision you ask for. You can't write them all down because they're infinite, but you can compute any finite part of them.
Ah, okay. There's a definite process to generate them.
Exactly, a finite mechanical process. He also made an important point about the size of the set of computable numbers.
How big is it?
Well, we know the set of all real numbers, including uncomputable ones like Chaitin's constant, is uncountably infinite. Cantor proved that you can't list them all out, even in theory.
Right, the diagonal argument again.
But Turing points out that the computable numbers are innumerable, or countably infinite. This means even though there are infinitely many of them, you can theoretically list them out. You can assign each computable number a unique natural number.
So it's a smaller infinity than all real numbers.
If you want to think of it that way, yes. A specific listable subset of infinity. And one more really important thing he stated. Any function of an integral variable defined recursively in terms of computable functions is computable.
Okay, that sounds technical. What's the gist?
It basically means if you have building blocks that are computable and you define new functions by combining those blocks using recursion, or a function calls itself, the resulting function is also computable. This is absolutely foundational for programming. It's how we build complex algorithms from simpler, proven steps.
Got it. So complex computable things can be built from simpler computable things.
That's the essence of it.
So pulling it all together, while Turing showed us these fundamental ironclad limits, the halting problem, the Entscheidungsproblem, the realm of what is computable is still incredibly vast and powerful. It forms the basis of literally everything we do with computers today.
Precisely. His work essentially drew the map. It showed us the boundaries of the computationally possible universe.
Knowing where the borders are is just as important as knowing what's inside.
It allows us to focus our efforts on what is achievable and, maybe more importantly, to understand why certain problems seem inherently, permanently hard or even impossible for any purely mechanical process to solve.
Okay. Now, as brilliant and foundational as this paper obviously is, we should probably also talk about, the critical reflection part. What didn't it solve?
Right.
Or what are the nuances, the caveats?
Yeah, right. It's crucial. Turing defined computability in this incredibly rigorous way, but yeah, it didn't magically solve every problem out there.
No magic wand.
No. Instead, maybe even more profoundly, it clarified what cannot be solved by a general mechanical process. It revealed these intrinsic limits.
Eliminating the darkness by showing where the light can't reach.
That's a nice way to put it. And he also drew this subtle but really important distinction between computable numbers and definable numbers.
Computable versus definable. Okay, what's the difference?
He noted that not all definable numbers are actually computable.
Wait, How can something be definable? Like, you could describe it perfectly in words or symbols, but you can't compute it. That seems weird.
It is a bit mind-bending. Think about paradoxes like Berry's paradox, which is similar to the smallest positive integer not definable in fewer than 20 English words.
Uh-oh, I see the problem. That definition itself uses fewer than 20 words.
Exactly. It's a self-referential contradiction. Turing's work touches on these limits where something can be clearly defined, semantically unambiguous, but that definition doesn't automatically guarantee there's a step-by-step mechanical process, a Turing machine, to actually calculate or construct it.
So there's a gap between description and calculation.
A fascinating gap. It highlights a boundary between language, logic, and mechanical computation.
Interesting. What other nuances did Turing himself point out?
Well, he was remarkably self-aware, actually. He noted that his arguments for the extent of computable numbers, the claim that his machines could capture everything we intuitively think of as computable.
The idea that any algorithm could be done by a Turing machine.
Right. He admitted those arguments were fundamentally appeals to intuition and for this reason rather unsatisfactory mathematically.
He admitted it wasn't a formal proof.
He did. This is basically acknowledging what later became known as the Church-Turing thesis. It's a thesis, a hypothesis, not a mathematical theorem. It posits that Turing machines, or equivalently lambda calculus or other models, fully capture our intuitive notion of effective calculability.
But you can't formally prove an intuition matches a formal system.
Exactly. It's a connection between the formal and the informal. It's a kind of philosophical leap of faith, although it's one that has been overwhelmingly supported ever since. No one's found a convincing counterexample of something clearly computable by algorithm that a Turing machine can't do.
So a very, very well-supported thesis.
Extremely well supported. He also mentioned another fascinating, often overlooked caveat related to real numbers. He said, Dedekind's theorem does not hold in the ordinary form if we replace real throughout by computable.
Dedekind's theorem rings a bell from analysis.
Something about limits. Yeah. It essentially guarantees that if you have a sequence of real numbers that's always increasing but never goes above a certain value, it's bounded, then that sequence must converge to a specific real number limit.
Okay.
But Turing pointed out this doesn't necessarily hold if you replace real numbers with computable numbers. You can construct a bounded, increasing sequence of computable numbers whose limit exists, but that limit itself is not a computable number.
Whoa. So the computable numbers are sort of gappy
Mm-hmm.
compared to the reals.
In a specific mathematical sense, yes. They don't have the same completeness property as the real numbers. These are subtle but important technical distinctions. And of course, we always have to remember the big caveat. The Turing machine is a theoretical model.
The infinite tape.
The infinite tape being the main one. Real computers always have finite memory. But that infinite abstraction is what allows the powerful universality proof and the clear delineation of computability limits without getting bogged down in physical constraints. It's an idealization.
Got it. Theoretical model, not an engineering blueprint. One other thing, the Gödel connection. You mentioned Turing referenced him, but how are their results really different? People sometimes lump them together as just limits of math.
That's a really important clarification to make because they are often confused. Turing himself explicitly says in the paper his results are superficially similar to those of Gödel, but quite different.
Okay, so how are they different? Let's break it down.
All right. Gödel, as we touched on, proved things about the inherent limitations of formal axiomatic systems.
Rule books, like for arithmetic.
Exactly. He showed that within any sufficiently powerful and consistent rulebook, there will always be statements that are true according to the intended meaning, but you simply cannot prove them using only the rules given in that rulebook.
True, but unprovable within the system.
Key phrase, within the system. He also showed the system can't prove its own consistency. It's fundamentally about the limits of formal proof and self-reference within a fixed logical framework.
Okay, limits of proof systems. What about Turing?
Turing, on the other hand, proved something different but equally profound about the limits of computation itself. He showed there are problems that are fundamentally undecidable by any mechanical procedure, by any algorithm that could conceivably be run on his idealized machine.
Limits of algorithms, not just specific rulebooks.
Exactly. While one major application of his result was to a question about provability, the Entscheidungsproblem showing no general algorithm exists to decide provability, the core result, the halting problem, is about the limits of what algorithms can do, full stop, regardless of the specific logical system they might be operating in.
Okay, let me see if I get this. Gödel. Our rulebooks can't prove all truths within themselves? Turing. No rulebook, no algorithm can even decide certain yes-no questions.
That's a pretty good way to put it. Gödel's is about the limits of static proof within a system. Turing's is about the limits of dynamic computation of any possible algorithmic process. They both reveal fundamental boundaries, but in complementary domains, logic and computation. Together, they paint a much more complete picture of the inherent limitations of formal reasoning and mechanical processes.
Okay, that makes more sense. Different kinds of impossibility. So, thinking about the impact, what doors did this incredibly foundational research actually open for the future? How did it ripple out into the world we live in?
Well, it's hard to overstate it, honestly. This paper didn't just solve an abstract logic puzzle. It quite literally invented the theoretical foundation for the entire field of computer science as a distinct academic discipline.
It created computer science.
The theoretical basis, absolutely. But the Turing machine became and remains the bedrock concept for everything. Algorithm design, complexity theory, programming language theory. It all rests on this foundation.
Every algorithm class starts with Turing machines.
For good reason. Every computer program you run today, seriously, no matter how complex, from your web browser to the AI generating images, can theoretically be simulated by a universal Turing machine. It gave us, for the first time, a formal, rigorous definition of an algorithm. Before this, it was just an intuitive idea. Turing made it precise.
The universal grammar of computation.
That's a perfect way to phrase it. It's why it's still taught, still relevant nearly a century later.
And beyond just pure computer science, did it influence other areas?
Oh, definitely. It had subtle but profound impacts on fields like artificial intelligence and cognitive science.
AI. How so?
Well, Turing's very choice of phrasing describing M configurations as analogous to states of mind subtly hinted at the possibility of mechanizing thought, of artificial intelligence. It suggested that maybe even complex human cognition could, in principle, be broken down into these elementary, simple operations.
If human computation is mechanical, could a machine replicate it?
That's the question it implicitly raises. It paved the way for thinking about minds, both human and potentially artificial, as computational processes. His later, much more famous work on the Turing test, can a machine's conversation be indistinguishable from a human's, stems directly from this foundational idea of mechanically simulating intelligence. The 1936 paper laid the groundwork for even asking if a machine could think by first defining what it means for a machine to compute.
Wow. Okay, setting the stage for AI decades later. All right, let's do it. Let's venture into the speculative corner. Given everything we've discussed, what truly wild doors does this research open for our imagination, even now?
Okay, speculative hats on.
If every computation can, theoretically, be broken down into these simple mechanical steps,
Yeah.
what does that imply about the universe itself? Could you think of the entire universe as just a giant Turing machine,
Yeah.
endlessly computing its own future based on some fundamental physical laws, the program, and the state of everything, the tape?
That's a huge idea, the computational universe, or digital physics. It's not just fringe philosophy. Some serious physicists and computer scientists explore this. If the laws of physics are algorithmic,
Then the universe is computing itself.
potentially, yeah, it suggests a kind of profound determinism, maybe, at the most fundamental level. Reality is an ongoing computation. It definitely challenges our intuition about what reality is.
Okay, that's one direction. What about the other side? The limits. We know some things are uncomputable, like the halting problem. But what about problems that are computable but just seem incredibly hard?
Yes. Efficiency. That's where modern complexity theory really comes in, building directly on Turing's foundation. His paper defines the boundary of computability, what can be done, period.
Yes versus no.
Right. But it doesn't say much about how long it takes. Something might be perfectly computable in principle by a Turing machine, but it might require an astronomical amount of time or memory, more time than the age of the universe, or more memory than atoms in the universe.
The difference between theory and practice.
Exactly. Complexity theory studies this, the feasibility of computation. Problems like the famous traveling salesman problem, or predicting how proteins fold, or factoring huge numbers.
They're computable.
In principle, yes, there are algorithms. But for large inputs, the time these algorithms take grows so incredibly fast, exponentially, often that even the fastest supercomputers on Earth couldn't solve them in a practical time frame.
So computable doesn't mean solvable in reality.
Not always. This distinction is crucial for everything from logistics and drug discovery to, very importantly, modern cryptography. Things like RSA encryption rely on the fact that multiplying two large prime numbers is easy, computable quickly. But factoring the result back into the original prime is incredibly hard, computable, but infeasibly slow without the key.
Complexity creates security.
In many cases, yes. Turing set the stage. Complexity theory explores the vast landscape within those computable boundaries.
Okay, one last speculative thought, maybe pushing the boundaries a bit. The halting problem. Turing proved it unsolvable within his framework, the classical computing model. But could we ever find a way around it?
Ooh, bold question.
I mean, what if new physics emerges? Or what if non-classical computation models, like maybe quantum computing, push to some theoretical extreme, or even more hypothetical ideas like hypercomputation using infinities? Could they offer a different kind of mechanical process that somehow sidesteps the limitations Turing proved?
That's deep into the weeds of theoretical computer science and physics. The standard view is that even quantum computers, while potentially much faster for certain problems, still operate within the Church-Turing thesis framework. They can't solve uncomputable problems like halting. Hypercomputation is mostly a mathematical construct, exploring what-if scenarios beyond physical reality as we know it.
So, probably not.
Based on current understanding, the halting problem seems truly fundamental for any physically realizable computation. But who knows what future discoveries might reveal about the nature of reality and computation? The paper definitively proves it within its defined framework. Questioning the framework itself, that's where science gets really interesting. Even if the answers remain elusive, it keeps pushing our curiosity.
Keeps us asking, what if? Okay, let's try to wrap this incredible journey up. Can you give us the TLDR on Turing's 1936 paper?
All right, the nutshell version. Alan Turing's 1936 paper on computable numbers basically gave us the conceptual blueprint for all modern computers, the theoretical model we now call the Turing machine.
The universal computer idea?
Right. He rigorously defined what computable actually means, taking it from a vague human intuition to a precise mechanical process. And in doing that, he proved two absolutely monumental impossibilities.
The big limits.
The big limits. First, the halting problem. There's no general universal algorithm that can tell you for sure if any arbitrary program will ever finish running or just loop forever.
Unsolvable.
Unsolvable. Second, the Entscheidungsproblem, Hilbert's grand decision problem. There's no general mechanical process, no algorithm, to automatically prove or disprove any given mathematical statement within a formal system.
Also unsolvable. Defined computation. Proved fundamental limits.
That's the core takeaway.
So this paper, it doesn't just teach us what computers can do, but maybe even more profoundly, it teaches us what they can never do, at least within these fundamental mechanical limits. It really sets the fundamental speed limits of knowledge, the boundaries of what we can ever expect from any purely algorithmic or mechanical process.
Well put.
So next time you're interacting with your phone, your laptop, any tech really, maybe take a second to remember that you're basically witnessing the practical, physical manifestation of a purely theoretical machine, an idea that existed only in the abstract, on paper, almost a century ago. It's just a testament to the incredible power of pure foundational thought.
From abstract logic to the device in your hand.
Exactly. And it really makes you wonder, doesn't it? What fundamental limits are we maybe bumping up against today? In AI, in our understanding of physics, in math? What are the things that might become the undecidable problems for the next generation?
A thought to ponder.
Well, we really hope this deep dive into Turing's absolutely groundbreaking work has given you some serious aha moments, maybe a new appreciation for the hidden theoretical gears turning behind our digital world.
And if you're now buzzing with even more questions than answers, and we certainly hope you are well, that's exactly what we love to hear. Keep exploring those questions, keep questioning, and definitely keep digging deeper.
Until next time, stay curious.